Hello, everyone. My name is Andrei, and I'm glad to see you all at this session on Winter Data Meetup organized by DataZen and Comday communities. And today we meet Jesus Rincon, an expert ready to show you how quantum computing is transforming machine learning and pushing the boundaries of AI. But before we jump into this session, I'd love to take a moment to ask you for your support in growing our community and recognizing our speakers. If you are enjoying today's discussion and want to stay updated for upcoming events, please hit the like and subscribe buttons below. Your participation not only acknowledges our efforts, but also helps us reach a wider audience, allowing more people to learn from these insightful discussions. Also, on the talk page, you can share your feedback, award speaker a badge, and rate the session. And your input is incredibly valuable. It helps us improve our future events and ensures our speakers get the recognition they deserve for their hard work. And we'd love to hear from you through the talk. So please post your questions to the chat and we will answer them during the Q&A session at the end of the presentation. So now let's welcome our speaker, Jesus, to share his valuable insights on quantum computing with us. Jesus, the floor is yours.
Thank you, Andrei. Thank you for that beautiful introduction, and welcome everybody to this talk that we have decided to name From Qubits to Machine Learning, Understanding Quantum Innovation for this Winter Data Meetup of this year. Now, our main goal for this is to introduce you all to this beautiful topic that is quantum computing and also quantum machine learning, because I know these words are so hot topics, so trending that most of you probably have either curiosity or you're afraid of that. So let's make this talk an introduction to this and a way to learn and be excited about something new. So please feel free to write all your questions in the chat, like Andre say, and let's begin. So before anything, let me give you a brief introduction about who I am. Like I mentioned, like Andre mentioned, I'm gonna be the one in charge of this talk. And why is the reason of that? Well, like it's the first word you can see there is I'm a physicist. So I'm a physicist with a master's degree on condensed matter physics, which basically allow me to study superconductivity. Now that doesn't sound like quantum computing, but because there is no enough tag to see the symbols between the fields of physics, the amount of mathematics I learned and the amount of physics I learned are highly correlated to what we see in quantum computing, allowing me the ability to swiftly translate my physics knowledge in superconductivity, which is actually, spoiler, a highly used thing nowadays in the industry, to this beautiful topic. Like, as I mentioned, I'm a software engineer here at EPAM. I do a lot of backend data engineering stuff, processing. So I also am knowledgeable about that. So please, you know, give me a ping if you need that. This is shameless promotion. I'm also an independent musician. I have my own songs on Spotify, um, YouTube, any platform you like. And last but not least, I'm also a nerd. So if you want to talk about anything else that you feel like, it's not work related, anime, science, math, or at all, please do it. For that reason, here are my links. My Instagram, which I mostly post my music. My GitHub, which is not that popular nowadays, but on the future I will populate it with more, hopefully, quantum machine learning stuff and quantum computation stuff, as well as data stuff. So I'm gonna keep you updated on that. And LinkedIn, which is where my most professional part. So that's where I promote this type of events, my professional growth and stuff. So again, please feel free to follow me here. Now, let's also let me remind you, like Andre say, and like every other speaker has said previously to me, please join these communities, DataSend, which is where we have globally all the ability to learn about data, not only about quantum computing, but also about uh, machine learning, data processing, databases, and much more. So please join this community. And if you're in LATAM, how I am, please join the DataSend LATAM community, like our previous speaker was part of. So please join our communities to be more aware of what we're up to and not only have more knowledge and more information about quantum computing, but also about data in general. Now, let me walk you briefly to our agenda today, which I have the audacity to call microscopic agenda because quantum is related, as I'll explain later, to microscopic things like atoms and molecules. So, first of all, we need to have a ground up idea of what we're speaking. So, we need to know the difference between classical mechanics and quantum mechanics. Then, of course, this is a new branch of physics for most of you. So, I'm gonna try to explain to you the basic concepts, mostly related in linear algebra, which is gonna be the basis for quantum computing in overall industrial applications. And then we're gonna start talking about the qubit, which, spoiler, I'm gonna say this a lot throughout the talk. I love the qubit because it's one of the simplest, if not the simplest, form of system you can have in quantum mechanics, but it has a ton of applications. And because of that, after learning quantum properties using the qubit, we're also going to know the differences between the bit and the qubit, because of course there has to be differences, not only because the one has quantum and the other one doesn't, but also what they can achieve and what they can't achieve. After that, we have our grounded level. I'm going to briefly explain to you what is quantum machine learning and hybrid computation, um, and what we can do with that, and also some applications that we can use with that in order to, have a brighter idea and a bigger scope of what's going on and what we can use this in the future. Finally, I'm gonna I'm gonna talk you to some companies of the huge amount that is, well, not huge amount, but it's really not that handful. It's more than a handful of companies that are working on this, and not only applications in quantum machine learning, but also applications in the broad spectrum of quantum technology. So if you're not only interested in quantum machine learning or in data in general, but wanna jump into something else, you also see more applications here. Now let's get started. Now, I believe we all went to high school. We all learned Newton's laws of motion. Well, that's basically what encapsulates classical mechanics. Everything that quote unquote slowly, which is far slower than the speed of light, and can be modeled using Newton's laws of motion, that is what we call classical mechanics. So ourselves, and this jar here, this bottle here, our phones, etc., can be encapsulated using classical mechanics. And even though it's not quote unquote as fancy as the word quantum, it actually encapsulates like 95% of the universe. So it's really useful using it. If we increase speed, though, if we go closer to the speed of light, we go to what I like to call Einstein's realm, which is relativistic mechanics, which helps us model light, planets, cosmology, etc. Now, what if we go to a quote unquote slow environment, but we decrease our size? How small would you be asking? Well, like I spoiled previously, to the size of an atom, to the size of a molecule. That's when we go to the realm of quantum mechanics. And this is one of the 5% that classical mechanics cannot explain, because, as I'm going to explain later, when it's needed, atoms behave quite differently than we expected using our classical mechanics. But if we want to know more about particles, their properties, and some information that can be known using this non-relativistic theory, we go closer to the speed of light to quantum field theory, or I like to call it relativistic quantum mechanics. Basically, in that realm of physics, we're gonna learn the properties, find particles, etc. So if you like CERN, you like relativistic quantum mechanics or quantum field theory. But we're focused on this on the end, on the lower left corner, quantum mechanics. That's gonna be a lot. And just like classical mechanics is actually really powerful on its own, and it's the main reason why we can use this to model quantum mechanics. Now, I already mentioned one that the first one, classical mechanics, uses Newton's laws of motion, and it's focused on a macroscopic scale. And the same thing happened with the quantum mechanics. It's at a microscopic scale. However, because of this microscopic scale, physics changed a lot, that we need to use different frames of reference or frames of work. One is the Heisenberg frame of work, which is mostly focused on linear algebra, and the other one is the Schrodinger frame of work, which is the one that's focused on calculus. Why do we have these frames of work if at the end of the day we can simply agree that physics is, universal? Well, that's because we have this thing that we learn or we have heard before, the particle wave duality. So poorly explained because there's much more to it. The calculus one focuses on treating particles as waves, and the linear algebra one focuses more on particles behavior. However, they encapsulate the same. For that reason, whenever we do classical mechanics, we will only be doing calculus. So whenever we have like this equation, the one we have in school, sum of forces equals ma, we need to solve that to basically understand our environment. However, when we do that in quantum mechanics, we will have two approaches. Another, and this is probably in my opinion, the hardest part to deal with regarding quantum mechanics is that quantum mechanics is highly counterintuitive, while classical mechanics is highly intuitive. What do I mean by this? Well, I can put this bottle to spin, right? And yeah, sure, we don't know what momentum it carries or what speed it has, but we can imagine this movement, and because of that imagination and using the Newton's law of motion, we can eventually predict and find all the information of this in a deterministic way, meaning that we can predict not only how this spins, but where it would be it at a given time. Unfortunately, our atoms can be counterintuitive. For example, this effect that you probably have heard of, the quantum tunneling. That's a really highly counterintuitive thing because imagine you're walking, right? And you're a solid thing, and suddenly because you can and suddenly you can phase through that, you can phase through that solid object. That is really highly counterintuitive, and that's because matter at that scale also needs to be treated as wave. So if you think of a wave that eventually passes a barrier, which happens, that would make sense, but this is a solid object. Atoms are actually solid, and because of this wave behavior I mentioned, this wave actually doesn't carry energy like classical waves. It's actually more of a probabilistic wave, meaning that this wave that I just mentioned uh, is the reason why it can be simultaneously here and then pass the wall. That is, and for that reason, it's a random state. So we're dealing with a lot of randomness, and that is natural of atoms, and there is nothing we can do. Now that we know that, like I mentioned, we're gonna focus on linear algebra because in quantum computing we like more of this particle approach. So I hope most of you have gone to college and remember your linear algebra classes. So linear algebra is really powerful because we can model every system like a matrix and every property of our atom or molecules, which we're gonna call states, as vectors. So what matrices hold are the information of what we want to measure, meaning energy, momentum, etc. And for that reason, whenever we tackle that to the state related to that, and we do the classical matrix vector operation, we're going to have this eigenvalue. That eigenvalue is a real number that contains the information of the property we're measuring, meaning that if we want to know about energy, spin, which we're going to define when I get to the next slide, momentum, etc., is going to be represented in here. And the vectors represent something else regarding the randomness of the system. I know this is really high level stuff and I'm not dwelling that much into it, but I just want you to be following me and have this walk among us. So, like I mentioned, we have all the vectors, we call them states, which is here. And we use this symbol which is called ket. Now, this is just, again, a visual representation of a vector, only that these vectors can be really huge and contain a lot of information. Now, these vectors can be represented also as linear combinations of one of two or more vectors, like we're seeing here. And one property that I like to define now, because I'm going to use it later for one of the coolest properties that we can have on quantum computing, is the spin. The spin is simply a property where atoms can have an inner momentum that it's basically represented as a spin that can go either up in this direction or down in this direction, which is basically represented here. And it's useful for actually creating qubits. And because we have a linear combination, as we know from our linear algebra classes, we also have coefficients regarding these vectors. These coefficients are related to the randomness of the system. Therefore, there is a they're related to the probability of the system. Like you can see here, it's a complex number, so then we need to make it a real number to have a probability, which is something that I'm going to explain actually now. In order to have that probability, we just need to do a projection of the state with another state that we need to measure. That will give us this coefficient square, giving us the probability. And since we already have the content of the matrix in the eigenvalue, we now have the energy associated to that state with its probability of obtaining it. Can we guarantee or not having that value we have? Well, sorta. And in order to answer that sort of, let's talk about, like I said, one of my favorite systems to talk about, which is the qubit. The qubit is what is called a two-state system, and that's a simple way of saying this. One of the states will be a zero, and the other one will be a one. And actually, spoiler, we can represent spins like zeros and one using the up state as the zero and the down state as one. This is the common notation we use in quantum computing. And we now have a linear, and we have now a linear combination that represents all the probabilities associated to our qubit or our quantum bit, which is basically the full name of the qubit. And like I said, we can start twitching these values here, these coefficients, right? So how many combinations we have of this? We have two? No, we probably have more than two. We have almost infinite combinations, and that's why we use this physical representation called the Bloch sphere. The Bloch sphere basically takes all of these coefficients and maps them out here and gives us all the possible information that we can process using our qubit. Now, this is useful because for some processes like finances or molecule creation or obviously data and machine learning, we might or not, that depends obviously on the problem, but finances, for example, demands that we have a preferable value or a preferable result when we're doing this. So we can start tweaking these coefficients to have that. For that reason, let me introduce you now officially to superposition. Before I do that, let's jump to what is called its classical equivalent, which is our voices. So whenever we speak, we have different frequencies, and they are all sum up. That is superposition, and that is the same in quantum mechanics. The difference is what happens. You're hearing my voice, and that's already a superposed wave. But when we do what happens in quantum computing is that of these two results, we're only gonna have one, the one that's measured in the projection I just measured, because the waves collapse on itself. And using the Bloch sphere, we can start Mendeling using the combination that we need to have the result we have. But that's cool and all, but most of you that don't have any knowledge prior to this will be saying, okay, Jesus, that's cool and all, but how can I use that for an effective measurement? Well, fortunately, we have quantum interference, which is the same again as classical interference. So let's explain classical interference. Classical interference is basically summing up amplitudes of waves, which will be these coefficients in our quantum case. And when we do that, we're going to make sure that one of the waves is going to be more prominent than the other. So if you have a guitar, for example, and you play a string, and that string has a natural frequency associated to the note it's playing. So that's an interference because we're making sure that the frequencies of the E note, for example, are the ones that are more prevalent. It's the same thing here. We're gonna start doing processes like adding, subtracting, using something called quantum gates, which is I'm gonna define later. that allow us to sum, subtract, and change our amplitudes and our positions to make sure that, for example, the finance case I just mentioned is more prevalent. So that way we can start tuning. But what most of you will be thinking, that's cool and all, but I'm just seeing more problems in quantum computing than classical computing. And you're right to a certain extent, but one of the things that superposition and interference allow us to do just for their quantum properties is that we can start simultaneously processing information. Say we assign to the zeros of our qubit losses and the ones earns. So now we're seeing simultaneously the growth of earns and the growth of losses. So we are not wasting time and we can model and optimize our time. But there's something extra in order to power this interdisciplinary branch that is quantum computing, and that is quantum entanglement. I'm sure, or some of you probably heard of the last year's Nobel Prize, which was related to this field of finding physically. So doesn't have a classical equivalent. So please let me try to give you an analogy that works. Imagine all of you have a twin sibling, and you're really close to that guy. You're basically hanging out. He's your best friend, or she's your best friend, whatever. And suddenly, for reasons, work, whatever, pursues, he decided to move to another country. Let's say I'm in Colombia, so let's go to Japan, which is a really long flight from here to there. And one day something's tweaking inside your head, like, how's my brother doing? I don't have time to call him because I'm really busy with work, but I'm gonna ask my mom to call him. And she calls him, and indeed something happened to him. He might be sick. He injured himself. Something like that happens with entangled particles. So entanglement, now in the low level definition, means that when a system is born with two particles, they need to guarantee that all of the properties are conserved. Let's go with the spin. So if we create two electrons, one needs to be born with one up state, one 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 up spin, and the other one is an down spin, right? And we put them far apart, far apart. And since we need to conserve all the properties of the system, no matter how far apart it is from each other, whenever we change the spin of one, say this one's up and this one's down, whenever we flip this one to down, this needs to flip to up in order to keep that conservation of spin in this case. And that is really powerful because when we entangle system, information starts to grow. And in order for me to explain that cool, let's talk about the differences between qubits and bits. So, like we mentioned previously, and let's go over for that because I want this concept to be as clear as possible. When we process with a qubit, we only have a binary thing. It's either 1 or 0, depending on how we assign it to our logical gates. And we also said that a qubit is always superposed, meaning that we can always have simultaneously, prior to measurement, the values that we want to have regarding the 0 or the 1. Bits scalar linearly. Makes sense. Our processors and our computers scaling linearly. Well, processors not, but that's a conversation for another day. But we need to sum them and they start adding that information linearly. However, thanks to entanglement, when we start to entangle and adding qubits, they grow to this number I put 2 to the n. That means that if you have 3 qubits, you have 8 bits. Now, if you have 5 qubits, you have 32 bits. See how it grows exponentially? And they need to share information all the time. So that way our processes for finances and stuff will be more powerful. Like I mentioned, one uses logical Boolean gates, like we all know, and the other one uses logical gates based on linear algebra. These logical gates have their names, but are basically an equivalent to this one that are matrices that change the properties of the zeros and the ones that we model in our original state. In more computation, because the history of the computation is broader than this, the bits are current inputs. So that's why we always need to keep our computers with electrical current. And that electrical current is used for a lot of things. However, because quantum computing is more on its genesis than anything else, we need different types of qubits for different processes. So we can create them with electrons, photons, superconducting stuff, etc., etc., etc. So it really is going to be more focused on what we need. For that reason, one of the advantages of classical computing is that it's multi-purpose and fast for simple processes. Meaning that if you want to do your classical summation, your classical multiplication, or a quick algorithm that you know is not going to take that much time, please don't jump to that quantum computer. Just keep using your old classical knowledge. It's never going to get old. It's always going to be useful. What is the advantage of, of quantum computing then? Big processes, big things, big and complex things because of this power of the 2 to the n scaling. That's where quantum computing starts to shine. However, that is not our only shortcoming regarding quantum computing. We also have one huge and more powerful foe to tackle to have a more productive systems in quantum computing, which is called physics. Yes, our computers are basically functional in every room temperature, so they can work here on a mountain or in the beach. But if we take a quantum computer, which we're gonna look at later, um, they probably won't have the same advantage because just by increasing the heat or moving the system, we are generating decoherence. What is decoherence? Is when you destroy the quantum properties of a system. It's basically what allows us to, yes, to collapse the wave to the value we need, but it's also the reason why, if it happens prior to our measurement, these machines are going to be quote unquote useless. So this is something that a lot of scientists and people are working nowadays to overcome. And this is physics. This is not money thing, unfortunately. Now, let's get to the gist of what most of you want to know. What is quantum machine learning? Why is this so important, at least in my head? Well, quantum machine learning is an interdisciplinary branch that allows to take quantum computation, algorithms, and machine learning to basically improve what's already known on machine learning. So we have a lot of things that we can do here. We have a lot of quantum equivalents that we can create for linear escalation, enhancing our models. But there are also other things that we can do that are not available in classical computing, at least not that efficient as quantum computing promises, which is, for example, quantum annealing. That's an algorithm that we can use to obtain, to identify the most optimal process in a way. So, for example, if we have a routing thing, traveling routes or distribution of things, quantum annealing will be our way to go. That's an application that we can use. Or quantum neural networks. As most of us know, quantum neural networks need a lot of processing information. They're really huge and they process a lot of things just to give us a result. And obviously, there is, and they may have a physical limitation thanks to that amount of information and the linear scalability that computers have. For that reason, thanks to what I explained about qubits, we can rewrite all of these neural networks to an equivalent using, of course, quantum computing algorithms and start processing. We also have the hidden quantum Markov models, which is basically a way for us to model data using a probabilistic model. So that way, if we have a huge amount of data, a huge data set, we can model it with these to see its pattern and get more information out of it in a graphical way, which is something important because all of these probabilistic methods may have a little bit of, you know, um, shortcomings the regarding their regarding their visualization and much more. We can do an kind of clustering, and thanks to this superposition, we can simultaneously work clusters instead of individually assigning them, improve our search algorithms thanks to quantum annealing, and obviously much more, etc., etc., etc. But there is also one extra thing. What I mentioned is a little bit far away of big industrial applications because, again, physics. That's our biggest fault right now. So there must be a way for at least to tackle this, and not without the need to learn a new computational language. And yeah, it exists. That is classical. That is hybrid computation. So hybrid computation allows us to write in our classical computer an algorithm in our classical language, say Python, C Sharp, C++, Java, whatever language is the one that you domain, using an SDK or your proper writing down for having the parameters in a way that a quantum computer interprets them, does all the processing, then it gives us an output in a way that our classical computer reads them and we can interpret the data in a better way. There is also another use of hybrid computation that is not in this image, unfortunately, which is using the power of classical computers alongside the power of quantum computers. How is that so? So remember I mentioned neural networks. Well, we all know that those have layers, right? Where we start doing processes. So we can add quantum layers to our neural networks in order to increase their performance, reduce their time of processing, etc., etc., etc. The latter, of course, providing we have the necessary amount of qubits and processing in a quantum computer. That way, we mix the best of both worlds. And let me briefly walk through you of just a few of the applications that quantum computer has. I already mentioned financial modeling because it's a really chaotic method, chaotic system, sorry, and we need a lot of processing just to get to know all of these, to see the best, to get all our information. Thanks to the superposition, like I mentioned previously, we can see results simultaneously, and also if we need to do forecasting or betting or selling actions or see how our market grows, boom, apply it. Forecasting also, because of the same reasons as finance, even though a little less chaotic, benefits from this because weather itself is really chaotic. So just predicting our weather nowadays because of phenomena like turbulence, uh, changes in current, changes in heat, etc., allows that to use these over processing, this rather no, not over processing, multi-processing and exponential processing to calculate this better. Like I mentioned with quantum annealing, logistics operation. So this way, we can find the best routes not only for cars but also for boats, traveling enterprises, etc., etc. Meaning that we can optimize not only the routes but also the resources we're using, gasoline, materials, etc., etc. Speaking of materials, quantum chemistry and quantum materials are really benefit from this because we need to model a lot of complex materials that our current computation stays a little bit down. So, in order for do this computational chemistry or materials, and yes, we will actually use a little bit of machine learning, but also other processes that I didn't have time to explain because time's so much, right? To do that. But the ones that probably most of you have heard is cybersecurity and cryptography, where if we don't make our systems quantum proof, or if we don't start creating new keys that are quantum based, anybody can use quantum computing thanks to this superposition to break keys that would take for a classical computer, thanks to its brute force method, millions of years to be broken, while to a quantum computer it may take from days to even hours, depending on how much qubits are available for you to use. And as you can see, there is a lot of things that we can do, not only for machine learning, like I just mentioned, with the algorithms, but also for much more areas that, yes, spoiler, and that's a fortune for us, most of these are actually fed by machine learning. So we need to take advantage of that. Finally, let's jump to one big gist, which is of course the runners of the big runners of this quantum race that we have nowadays. which is the first one is IBM. Like I mentioned, I work in superconductivity, and this is IBM's quantum supercomputer. This uses superconductivity as qubits in a really more complex process in using electrons, but not in the classical way. Now, the fun part is that they claim that by 2033 they're going to have a billion operating qubits. So industrial operations going to be possible, but they're trying to get to 100 million operations at this time. So they're running a lot for that race, and they actually done POCs and in no, actually mostly POCs, my bad, on things that you can apply like logistics or optimization using these computers. And if you want to learn more about quantum computing, and instead of listening to a guy at the back of your screen and rather get your hands on, you can also use Qiskit, which is their service for online processing and cloud services for quantum computing, where you can have tutorials and simulate your own quantum circuits in a graphical UI or using a Python SDK. The other runner I want to talk to you about is Xanadu. Xanadu is a Canadian enterprise that is focused on quantum computing, and they're the ones that are the first one to create a photonic processor. This photonic processor, because of Xanadu's um, tendencies, is mostly focused on quantum machine learning. So the photonic processors are mostly used for quantum machine learning. And for that reason, they provide a free SDK, a free tutorials in their website called Pennylane. This SDK is focused on Python, so please have your system, your, I don't know, your Visual Studio Code, your PyCharm, whatever you like to use, install it, and follow the tutorials to have an idea using our knowledge in Python be transcribed to algorithms that then we can turn into better POCs or better ideas for the future. And they're constantly growing. There's actually a lot of things I haven't mentioned you, like the amount of money governments are investing here and so much more. But finally, well, I believe that most of of the people in this talk is actually related to engineering works. So all of you know cloud, right? So the big providers of cloud that we all know and love are actually also in this race. GCP, Azure, and AWS. GCP and Azure actually have their own quantum computers and their own languages. In GCP's case, it's called the CirQ, and they also have a framework for TensorFlow called TensorFlow Quantum to run quantum machine learning. I don't recall which type of quantum computer they have, my bad, but they have it, and they actually run it, and you can access it via cloud. And Azure has their own language, which is called Q Sharp, yes, based on C Sharp, and also their own services that you can access to. And the three of them, because this is where AWS has a bigger advantage, uh, you can call other providers like D-Wave or Rigetti. They're also big runners in here. Rigetti, D-Wave also uses quantum annealing and photonic processors, if I recall correctly, and Rigetti is more focused on semiconductors, if I recall correctly. So you can use your cloud systems to have hybrid computation, writing your code in your preferred languages. For data, it's obviously, well, not obviously, but most of the time it's Python. So our Python code, we send it to the cloud, and then we're good to go. And we expect for the bill and the result to be for us to have. Finally, I would like to talk to you about more industries and applications we have. I already mentioned quantum chemistry and materials, and obviously we already talked about quantum machine learning, but there are more things that we can do, like full quantum software, so transcribing our things that obviously need that transcription to full code on full quantum hardware that also in development, doing our quantum simulation, also creating our full quantum cloud computing systems that we can call them via cloud in a more accessible way. Because as you saw in the quantum computer, with IBM, those things are huge and are actually highly expensive to maintain. So yeah, we need to have a better way to access them with via cloud and much more. um, and obviously all the other applications. So that would be all for this part. I know it was a short one, but we already covered a lot of it previously. That's why I didn't spend that much time here. So, as a closing statement, if you would like to join our community again, please follow these links that we have in this useful material slide. Like I mentioned, if you want to know more about quantum computing, not only in a theoretical way, but also in a hands-on way, please sign into not only Qiskit here, but also Xanadu and Google. They have these free models for you to understand. If you wanna go for a more lower level, which is something I highly recommend because most of these things still relate a lot of algebra and processes. Uh, I've also put this linear algebra course for you. It follows the basics only, focus on this type of matrices that we use on mechanics. And if you like this topic, not only for the quantum computing part, but also if you like materials, atoms, and stuff, there is also a free course given by Stanford University and actually a lot of top universities around the world on quantum mechanics. So you can watch this. And obviously, like I mentioned at the beginning of the talk, there's also my email and stuff. So if you need more communication or more material that I can provide to you, please reach out to me. Also, we have the AI UA community for you to join if you want to know, like I mentioned, we in data science we have more than just quantum computing. We also have data science, engineering, and analytics. So please join these two communities: the AI UI community and the AI BA stream community. Thank you everybody for listening. Thank you everybody for being here. It's been a pleasure, and I hope you enjoy and learn something new today.
Thank you, Jesus, for this great introduction into quantum computing. And we have a lot of questions from various chats. So let's try to address them because we have some limited time before the next talk. So the first question, are desirable computation tasks based on initial room conditions like temperature? Uh, Sorry, Jesus, you're on mute. Please unmute.
Yeah, my bad. So no, nowadays having room temperature conditions is not available. One of the actually main topics that researchers for physics, not only for computation, are working on is finding materials that can work on room temperature. This is called the room temperature superconductors. This is an ongoing research for a lot of institutes and industries around the world. But no, now we can not have them outside room temperature, unfortunately.
Mhm. Okay. Good. So next question. There are some questions, similar questions, so I will group them.
In one, yeah.
Uh, what about the cryptography? How quantum computing affects it?
So, like I mentioned, our current cryptography it's based on the fact that we need to use a lot of brute force to break all the keys. So, thanks to superposition, we can have our qubits. Uh, this is a poor explanation, but works doing brute force simultaneously to all the possible combinations to address this key. There's actually something called the short algorithms that allow us to break a number to its prime factors. And in cryptography, we're basically creating our keys based on that, on our prime factors. We use the short algorithms and all the other things in quantum cryptography that I forgot for now. My bad. I did a course on that. I forgot. My bad. That allow us to break it. So there are two approaches to this. The one I mentioned previously, which is create full quantum keys. Why? Because since quantum mechanics is fully random, then the keys we create are fully random. And even though, yes, they can be processed at a time with superposition, since they're fully random, it makes no difference because the computer is not having a continuous advance or doing post cryptography, which is enhancing our current systems and keys with backup algorithms to push that away, like
Mhm.
hackers or anybody that wants to introduce this. So those are the main topics, and those are the hottest topics right now because are the quote unquote easiest to apply in a near future. like by
Yeah.
2027, something like that. People claim they can apply the first quantum key.
Okay. So in other words, with quantum cryptography, we can take a hash and pass it through the quantum computer and get the password back immediately, or maybe all possible passwords which
Yeah,
uh, generating this hash, something
yeah, it
like that,
would take
as
like
I understand it.
yeah, exactly. It would take like days or even hours, depending on how much
Mhm.
power we have in our quantum computing. Correct, Andre? Yeah.
Uh, Another question from the chat, which resource you can recommend to learn about quantum computing and how to code in qubits?
Oh yes. So the one I put in this last one here, this is actually the QSKIS manual. It has a lot of things. Not only it has the access to their SDK, how to write our first code, how to work with qubits, and more advanced courses like the ones presented at Penny Lane or even at QSKIT allow you to write full-fledged algorithms using words instead of boxes. You will get the boxes when you watch the UI for QSKIT.
I also saw that Google offers some platform to
Yes, yes,
learn quantum programming and to
yes,
play with qubits, simplified ones, just to learn
yeah.
basics.
This one I put here, for example, the one that says quantum machine learning concepts, TensorFlow Quantum. They use it, but focus most on their TensorFlow Quantum library or SDK rather.
Mhm.
So fortunately, yes, there's a lot of resources. I just put these ones because I believe they're the most quote unquote accessible. But yeah, there are way much more, and there are a lot of repositories that want to apply this. Just to answer a joke that probably someone has, yes, there is somebody already make a repo to run Doom on a quantum computer.
Cool. So we would expect the next talk from you is some demo how to code and what can we achieve with a simple
Yeah.
quantum program. Okay, thank you. And other questions related to the size of those computers and complex environment we need to run them. So any chance we will have quantum computers on our desks or even in our pockets in near future?
Um,
What do you think
Probably
about
not in the near future because we're in nowadays in the race to find the superconductors at room temperature, which is a really complex race, and we're getting closer every day. That's something I want to say, but we're far off from having portable devices. So
it?
for a near future, not, but for a near future, which is possible, and this is something I'm praying for to have, is having them in a way in a cloud access. So I believe that the near future is going to be hybrid computation. So please learn quantum computing, but also learn Python a lot. It's going to give you
Hmm.
a lot of opportunities, in my humble opinion.
So you can take your phone, code some Python script, and run it in quantum cloud. Yeah.
Exactly, exactly, and actually,
Cool.
it's actually possible for with Xanadu, IBM, or even the cloud providers I mentioned previously.
Okay, and thank you. Also, we have some complex question. Let me try to shorten it. So, if we will consider a spiral shape instead of sphere, uh, which direction is for up spin in that case?
Oh yeah. Um, well, I like the sphere one, but it really depends on how you want to assign it because the spin we say it goes up and down, but we really as as humankind we have never saw it. So that we say it goes up, which will be here the zero, or down, which will be here the one. We use spheres because they're smooth and they're actually really cool to watch. But if you wanna portray this in a hexagonal way and put your plane in a hexagonal way for different combinations of spin, that's possible. And there's actually particles like bosons that allow you to have uh, interaction of different spins together or the same spin. So yeah, this is just for because spheres are symmetrical, so we can see the symmetry of the system easier. That's why we use spheres.
Mm. Just to simplify our representation of it,
Yeah.
right? But it can be much more complex, and in more complex systems, how we can get a binary result.
So for more complex systems, what would we will have will be multiple block spheres, and depending how we treat them, say the logical gates I told you about, they will have different values, and then we can rewrite them when we measure the system to their equivalent zeros or one, and then start using our binary methods to read that result.
Mm. Okay, got it. Thank you. And I think the last question we can address in this Q&A session, in the part when you discussed qubits logic, you've mentioned that logical gates are based on linear algebra, right?
Yes.
And it sounds like logical gates for quantum computers are similar to LLMs, because if we use linear algebra objects as logical gates, we have the same in LLMs. We have a set of matrices with some numbers which we use as probabilities to pass something through this network. And so here, LLM is just a logical gate. And in that case, what is the next? So maybe we can have something much more complex and more great
Elegant.
than AI here.
Yeah. Well, that's a good point. So yeah, the main difference between logic LLMs, which is are represented in vectorial spaces and they have their own matrices, is that we are using this to represent everything in quantum computing. And we're using the matrices not only to represent our results, but also to represent how to change it. So if we want to change the 0 to 1, we use a matrix. If we want to add them up, we use a matrix. If we need to scale them up, we use matrices instead. And not only, and we also use these matrices and vectors to represent the results. So it's a little bit more than that, but yeah, I actually believe that the guys that use LLM in their first papers were actually thinking about quantum mechanics for their work because it has a lot of physics grounded ideas.
Okay, thank you. So I think we are good with all the questions from the chats. And thank you, Jesus, once again for this great talk and fruitful discussion. And thank you all who joined this session and asked questions. And don't forget to say our speaker thank you by awarding a badge on event page and rating the talk. Be sure to subscribe to our channels to get more content like this. And we hope to see you on our closing session, which will start soon, right after this talk, on Winter Data Meetup 2025. Thank you all for your participation and engagement. Thank you.
Thank you, thank you everyone. Thank you, Andre. It's been a pleasure being here.
Bye.
Bye.